data analytics. And then in the afternoon, Ishan will do a quick thought session on the continuation of deep learning, morning deep learning, and then around 3, right? Just to what inform you people beforehand, around 3 we will go in for that online assessment activity. Okay. So we will share the link, right? And those of you who are not able to click on the chat room link, I will have my TS pass it on to your individual WhatsApp numbers. Okay. And so roughly 3 to 4, right? And then around 4 to 4:15 or 4:30, right? We will wind up. So that is the rough sketch for the day, right? Just to get you started on the first session's agenda, right? And I think that deep learning word has in fact these days become more famous than in fact machine learning, right? People start or have started viewing it as a separate area, right? But I think the first day is my Venn diagram, right? Deep learning is only one subset under ML, right? Or I view it as only deeper than a normal neural network. That's it, right? So, okay, right. So I think the focus of Ishan's session, right, will be on uh, uh, exposing you to the power of the deep learning, right? And I think that there are different types of networks in it here. A generative adversarial network, right? GANs as they're called, then CNNs, right? Convolutional neural networks, right? But I think he will possibly revisit some of the neural network concepts for a recap notion or for you to better digest the deep learning concepts, right? And just for the benefit of, I think you already possibly got it as well. Neural networks is a field, right? Has been there for a long time. Right? Possibly deep learning came and made it famous, right? Why is it called deep? Right? You just don't have any limitation on the number of layers that you constitute in between the input and the output layer, and then give it all to the PyTorch or Python, right? Libraries. Don't just bother about the weights, updates, right? All that stuff, and then come in for the best results, right? The accuracy, right, with your deep models, right, is far high when compared to the conventional neural models, right? And the other thing, neural networks as an area, right, or neural network based classifiers, I guess Ishan may touch on backpropagation. Okay. Backpropagation, right? For all, they had to have what extensive training, right, adjust the weights again and again, right, all that stuff. Right? But it did survive for a long time, or it is still in fact surviving for a simple advantage that the other classifiers, right? Whatever you take, KNN, decision tree, Bayesian, right? Many more you will have, right? All of them, right? If the input data is highly noise prone, or the input data is highly noise prone, best example I give is your image scenarios, right? Your biometric images, right? All that stuff, right? You possibly even the training images, right? You will have a lot of noise in it, but you can't ignore them, right? Neural network is best suited for highly noise prone scenarios, right? Because of its repeated learning or iterative learning, backpropagative based learning, right? All those variants, it adjusts to the noise quickly, right? So in fact, that is the way I use it's the case of neural networks. But I think these days deep learning has there are some places where deep learning is a course by itself, right? So I think Ishan will take care of the rest. And regarding Ishan Dash, he's a MTech a graduate from our institute, and he was also a best project awardee for the MTech project. And I think it was again related to something related to deep learning and GANs, all that stuff, right? So and then I think he has had a wide variety of exposure, right? During the second year, he was one among the few who was selected from at a country level, right? One among the 50 or 100 pan India who represented our institute at a youth parliament, right? And then he has also had a stint of internship at a Japanese university, right? Where he worked on a live industry problem from Hitachi or Mitsubishi, right? These two are the only famous names in Japan, right? So I think it is Hitachi, right?
Hitachi,
And
yes,
eventually
sir.
we did like Hitachi, right? Those are the only two names that strikes us, right? And in fact, his exposure there was also on deep learning for some auto-related packages, automobile, I mean, right? So I think his exposure, I think, to be very frank, my learning for deep learning came from Ishan, right? I was good at neural networks, but he was the one what brought me on to the generative adversarial networks, all those areas, right? So that is why the moment it comes to deep learning, my only falling upon shoulder is Ishan Dash, and I think later he also secured a long internship stint with AMD, which is a it's almost similar on par with Intel here. AMD is a famous processor chip manufacturing company, right? And I was very happy to note that this internship got extended to a project, and the project got extended to a offer, placement offer. So he's now a full-time employee with AMD Corporation, and he is on the research team at such an young age, right? And I think somewhere he's also fitting in deep learning in their research there, right? And the last 2 years he has been associated with AMD, and he possibly has also filed some patents along with their employees there, right? So I don't want to hold him for a long time because he has already requested for a 15-minute extension. So I'll hand it over to Ishan. You can take over. Thank you.
Thank you so much, sir, for
And
that.
you can start.
Yes, am I audible?
Yes, yes, yes.
Yes. So thank you so much, sir, for that warm introduction. So let me just start by presenting my screen. I think my screen might be visible now, right?
Yeah.
Okay, so we're having the fifth day of the workshop, that is Introduction to Deep Learning. So I think most part of my introduction was covered by sir. So I'm a software engineer too at AMD R&D India, right? So talking about deep learning before we actually get started with the session, it's a very fascinating domain, and I was particularly very interested. One second, am I seen on the video? Okay, probably I can just yeah. Okay. So I was particularly very interested in the domain of deep learning because of two reasons. One is, I mean, look around you, from probably mobile devices to the way how banks work, probably to the way how, most of the things work around us in terms of banking applications and fingerprint recognition or face recognition or the translation of one language, right, to another. We are actually surrounded by deep learning without being consciously aware of its power and its visibility. And the second part was, in spite of being so much surrounded by deep learning, there is so much research and development. The scope of research is so high, and that actually persuaded me to take up the research in deep learning, where my focus of my master's thesis was in improving the architecture of one of the deep learning networks, right? So getting started, so topics we'll be covering today will be artificial intelligence, right? So there's a lot of hot topics and hot terms that is randomly thrown around and used by people, AI, machine learning, deep learning, so and so things, right? So these jargons are pretty cool, and it's in today's scenario, if you're not aware of these jargons, probably it's high time to buckle up, right? But then the thing is, people are not aware of what actually each of these terms are, and how are they actually different from one another, right? AI, how is it different from ML? How is ML different from deep learning? Obviously these cannot be an alternative terms to each other, right? So there has to be some meaningful difference between them. So we'll be looking into all of those things, starting with what is artificial intelligence, right? And I'm sure in the past couple of sessions you might have been introduced to machine learning, right? So in my perspective, you just cannot kickstart the deep learning tutorial or deep learning session without understanding what machine learning is entirely. And there's a few limitations of machine learning as such, right? And that limitation is the very reason why there is something called as deep learning, right? So my endeavor would be to make a proper flow throughout the session, so that whatever you might have understood even in the past sessions, right, this session actually helps you connect all of those dots together to understand the bigger picture, right? So that is why I'm emphasizing on the flow, right? Even though it's an introduction to deep learning, I will start with what is AI, cover limitations of ML, then introduction to deep learning. Then there's a architecture of deep learning called convolution neural network. So we'll be looking into that and how it works. Then there's another architecture of deep learning which is called the reinforcement learning. And so basically I'm trying to cover two different networks, right? Or you can say two different types of deep learning. One is called the CNN and another is called the reinforcement learning. And then we'll be closing by looking at the RL application. RL is basically reinforcement learning, right? uh, before I actually start, so I just wanted to say I have this very peculiar habit of questioning or shooting the audience with some questions, right? So the purpose of this is actually it helps me understand uh, what pace should I go ahead with, for the rest of the presentation. Because when you are in a offline session, the audience reaction actually tells you a lot, but then in an online setup actually becomes difficult to gauge, right? What pace you should be carrying on. So I'll be asking a couple of questions here and there, and please feel free to unmute yourself and give the answer. So this will also help me make a smooth transition, right? There are so many different topics. Okay, so by asking few questions, it makes my job as a speaker to make the transition smooth and to understand what is your level of understanding on the other side, right? So we'll make it a little interactive. Okay. Yeah. So yeah, now coming to the importance of flow in learning, right? Now, whether a human is learning or a machine, see, we are basically trying to understand how a machine is trying to learn, and it is all at the end of the day trying to mimic the learning process of our human itself, right? Of the human mind itself, right? So whatever is the learning, whether it's a machine learning or a human learning, maintaining a flow in the learning process is very crucial, because the learning process itself is a very hierarchical concept, right? That is why whenever a human starts learning, whenever a baby starts learning, he starts to learn from alphabets, then to letters, and then finally he moves to sentences. So similarly is the case for artificial intelligence, where if somebody is introduced to artificial intelligence in the beginning, he has to be taught about what AI is and what is a broad concept, right? AI is a very broad concept, and it actually encapsulates many smaller, or you can say specialized domains, right? So before getting started, it's always essential to understand what AI is and what the broad concept is, right? And only then you are actually introduced to concepts of machine learning, right? So I'm sure we have already seen what machine learning is in the previous sessions, the classification and the clustering algorithms, right? Now, before we actually go into introduction of deep learning, it is, like I told before, it is imperative to understand what machine learning is and what are the different type of problems it can solve. Because turns out that if machine learning could do everything, then what was the need for deep learning, right? So there are some things which machine learning cannot do. We'll look into it, right? And that is where the need or the motivation for deep learning arises, right? So in any sort of workshop or any sort of tutorial you'll see, right, you will never be introduced to deep learning before machine learning. Because what happens, everything is a popular and hot term these days, right? And machine learning was very popular sometimes in 2010s and something like that, and only the last decade deep learning has taken over that hotspot of machine learning, right? So people are forced, or they get excited to learn deep learning even without covering the basics of machine learning. Okay, so I would actually suggest you people not to do that. And so that's why the introduction to deep learning session of this workshop is at the last day, right? So yes, getting started, what is artificial intelligence? So can somebody tell me what is this? Please unmute yourself and you can say what is this, just to make it more interactive. Hello. Anybody? Santosh, am I audible?
Yes, Session, yes.
Yeah,
Yeah,
I
you're
think
audible.
anybody from the audience probably can just say what is it. Even if, doesn't matter. We're all in the learning process, right? Even if it's wrong, we'll go and back to it. Yeah.
Yeah, AI just to develop some applications that should work analogous to human beings, just like activities that should perform activities analogous to human beings.
Correct. My question was, what is this image? You must have
Okay.
seen movies and stuff
Glass,
like that,
something.
right? So, hello?
Hi.
Hello?
Is it something related to Google Glass?
No, no, no.
Okay.
Okay, let
Hello?
me give you a hint. It's related to movies. Yeah.
Yeah, hello?
Yeah, hello. Yeah, tell
Yeah,
me.
it's Iron Man. Iron Man Jarvis.
Yes, yes,
Yes,
yes.
yes, yes.
It's Iron Man Jarvis. So good job. In fact, everybody who tried, thank you. So the interaction is very important. And this is Iron Man Jarvis, right? So you see, we have been popularizing artificial intelligence and machine learning and all those sort of hot topics, right? Through movies, through workshops and sessions, right? So you see, we are totally surrounded by all these things. But then the most important thing is to understand how does it work. You see, Iron Man, he actually gives some order, and then all his suit gets assembled, and then he does all sort of image processing to to know where to shoot the missile and stuff. It's not magic, right? So today we'll be unboxing what is there in that black box. So how does whatever he does, not particularly Iron Man, but whatever happens in AI, we'll try to understand that in a conceptual level, right? So thank you guys for answering. So before I actually start with what machine learning, what artificial intelligence is, what are the concepts and how does it work, I always start with applications of AI, right? Because this helps me as a speaker to get your attention, right? And form the curiosity, right? So we'll start with our applications. So, like any other machine learning or whatever you have seen so far in the session, it is used for predicting the future, right? So far, so good. The prediction of future can be anything. It can be. I'm hearing some noise. Could you please mute? Okay. Yeah. Thank you. Yeah. So it is predicting future. The future can be anything. The future can be predicting the sales of a or the rent or the cost of a house 10 years down the line, or predicting what sort of disease is there by looking at a medical image. So predicting the future can be anything. The second is the chatbot. I'm sure you all must have had some experience with chatbot, right? So Google Assistant is a form of chatbot. Siri again is a form of a chatbot, right? Where you can actually real time interact with the bot. It's a robot, right? And the robot, if you see, it doesn't give you random answers. Most of the time, it gives you something very, relevant to what you asked. So how does it do? Again, I think this was covered in NLP, and so this is one of the again important applications of AI. Then we coming to self-driving cars. Now, self-driving cars is the new hot topic going around, especially in the last 5 years, where people are predicting the next 10 years or so. We'll see self-driving cars where the cars will be capable enough to know where to go, how to avoid the obstacles, how to take a right turn, left turn, all that sort of things, right? So that is again one more application. AI eye doctor. So this is one recent development in the field of AI where this thing helps you to detect various sort of eye diseases, eye related diseases at a very early stage, right? And in fact, deep learning is very heavily also used in the domain of medical treatment, in the form of, you have this tumor and all those sort of related medical images, and deep learning can be used to actually tell whether no, yeah, there's a tumor in it, or is it a fair sample, right? So next we have something called as AI music composer. Now this might actually sound weird, but we do have something like AI music composer, which is at a very nascent and a very new stage, and it is used to generate music. And the most important part is it is used to generate the original music, right? So it's not like it is just copying something and reproducing. It is an original composition. Still a long way to go, right? So now finally coming to what artificial intelligence is, going by the definition, it's the theory and the development of a computer system able to perform tasks which require human intelligence, such as visual perception, speech recognition, decision making abilities, translation between languages, is called AI. See, humans, we are able to make such decisions, and we have these abilities even without consciously knowing what actually enables us to have these abilities, right? I mean, speech recognition and visual perception, these are things which comes normally to us as humans. But then to understand, to be able to transfer this sort of power to a machine, we have to actually understand what is the human behavior in understanding or in having these abilities, right? So we'll go much we'll go in detail. Talking about specializations, like I told you, when you start with AI, you should understand AI is a very, very broad topic, okay, and it has various subdomains, or you can say specialized domains, right? And so at a time we can only focus on one. So I think natural language processing was the session was taken yesterday or sometime back. So similarly, AI has many specialized domains. One of them is neural networks, okay, another is natural language processing, then there is robotics and reinforcement learning. So in this session I'll be covering neural networks and reinforcement learning, right? So this, if you want to understand what AI is, this is the simplest picture or the simplest Venn diagram that anybody can show you, right? Artificial intelligence. So before you start with the entire domain or the entire concept of AI, you start with AI. AI itself, which you understand is very broad and very, very basic to start with, right? And then there are multiple subsets. The first subset coming machine learning, right? So machine learning you can call the first subset of AI, which actually learns how to predict and learn the model. Okay, there are various types. You might have seen supervised, unsupervised, classification, clustering, right? I'm sure you must have all seen that the tutorials in the previous sessions. Now, since the entire session is about deep learning, that is why I always stress that there is something beyond machine learning, and that is where the deep learning concept comes, right? So deep learning is different from machine learning in the sense that deep learning uses something called as neural networks, right? And that neural networks is to simulate the human-like decision making. So machine learning is not about mimicking the human mind. Deep learning is more about mimicking the human mind, right? So yeah, what is machine learning? So I'm sure you must be knowing the answer to this, right? So machine learning is a type of AI that provides computers with the ability to learn without explicitly being programmed. Yeah, so classification, clustering, the association, rule binding, everything is a form of machine learning, right? So if you would have seen the data set what we had actually used for various sort of classification and those class level predictions, we had something like this, right? So you see the data set was a form of a table, right? Where you can say this 1 2 3 or something, where actually the inputs, right? And we had multiple columns where each column specified a sort of a feature, right? And then the last column was actually the class label. So the class label is what the machine was supposed to predict, right? And since this table is given as an input to the machine learning model, it was also called the supervised learning algorithm, right? I hope I'm clear so far. So that is all. I'm just trying to summarize what we have seen in the machine learning session, right? And then when you need to test the model to get predictions, what do? I have used this data set to train my model, right? Now, once the model is trained, I'm going to give a new input. The new input will have all these columns as in all these parameters. And based on these parameters, what the machine has used to learn, I'm going to be applying the same learning, whatever model I have learned in during the training phase. I'll be applying that on the input to get a prediction. Okay, so this particular input was actually classified to this particular flower type, right? So this is what the machine learning was in a nutshell. Now, again, I have some question for the audience. Probably you can mute and unmute and just try answering. So what input data types or formats did you see when which you can give to a machine learning model for prediction? Let me just make it a little more simple. So far we have seen various types of classification, clustering, and all those sort of algorithms, right? So what was the general input data type which you saw, or in what form the input was? Anybody want to take a try?
Discrete data sets.
No. Okay, discrete. What do you mean by discrete?
Some kind of tabular forms and.
Correct. Okay. Correct. Fine. Tabular form. Okay. What did that tabular form actually represent? I mean the table, right? I mean there must be columns and rows. So what did each row and each column signify?
Some attributes.
Some attributes. Okay. Now what do you mean by attributes? I'm not testing. I'm not testing. So don't be scared and all. I'm just trying to have an interaction so that it helps the entire classroom, right?
Yeah, maybe features, what was given as answers.
Yes,
Yeah.
yes. So each column actually represented a feature of that particular row, right? So it's and based on those feature, actually it helps me to make a prediction, right? For example, here we are talking about flower. I mean the classification of what type of flower it is. So we know for a flower to be of a certain type, there are different features: the sepal length, the sepal width, the petal length, the petal width, right? And using all these features, we can distinguishingly classify a flower into a particular category. Correct? So you see, every column actually specified a feature. Okay. Now, another question based on the previous question, right? So now, like I told you, in the applications of AI, we saw self-driving cars as an application of AI, right? Now, what is the input data type there, and can machine learning be used for that purpose? Now, somebody told me that tabular form is what was used as an input format, which was given to the machine learning algorithms, right? Now, can you tell me what is the input data type or the input format for a self-driving vehicle? Anybody?
Can it be images,
It can be images. Very good. Then,
videos?
yes, videos. Very good. Very, very good. So yeah, and then coming to the second part of the question, can machine learning be used for that?
Yes, machine learning can be used for that.
How? No, machine learning. I mean this.
It's because you have to train. You need to train the vehicle. Since it's a
Correct.
self-driving vehicle, what a human being cannot be. I mean, what it has to replace a human being. Right? So
Okay. Oh,
in that case, I think it's required.
okay. Okay. Thank you so much, ma'am, for answering. So coming to the first part of your question, yes, it is absolutely correct. The input type becomes images and videos, whatever the vehicle uses, right, as a sensor, right? But the second part, like I told you, you should understand what machine learning is not a very diverse field. It's pretty narrow, and when we come to deep learning, we realize it's even more narrow, right? So machine learning, if you see whatever classification and the clustering algorithms we have seen so far, the input data type has to be of the form of a table, right? This is a table, right? So the input has to be of a form of a table, where I explicitly give the machine various features or various columns, right? And that actually features helps the model to make a prediction. Now my question was actually, when you are giving an input as an image or a video, but the machine learning model is actually expecting an input of this form, but your image, can you model your image into this form? Anybody? You get the difference, right? I'm just trying to set a platform right before we actually go into seeing what deep learning is, right? So a machine learning model is expecting an input of the form in the form of a table, where you have multiple columns. Each of those columns is a features, and then you have a classification label, right? But when we talk about images, which is basically an input in the case of a autonomous vehicle, in that case, how are you going to convert the image into this table? You can't, right? So basically, for a machine learning model, you cannot give input as an image, image as an input. Forget image; it can be voice signal, or it can be a video, or any sort of image frames, right? You cannot give that as an input to a ML model. So answering this question, yes, the input type is image and videos, but then machine learning cannot be used for that, because it is expecting an input of the form of a table. But then how do you convert an image into a table, right? You cannot, right? Just imagine you are all in a real time scenario where you are in a self-driving vehicle, right? You have to take the input image and then convert it into a table. By the time you do all these things, the car has already crashed some sort of a pole, right? So you understand my point, right? So I hope the platform is set for understanding the limitations of ML. So now we'll be looking at limitations of machine learning and which actually paves way for motivation for deep learning, right? So whatever we have seen so far is machine learning, right, where we have the tables and all that stuff and we have a classification. But now we'll be digging deep into deep learning, right? So there is a clear difference between deep learning and machine learning. That is what I'm trying to make it clear. Now there are certain limitations of machine learning, right? So the first limitation is machine learning cannot solve some artificial intelligence problems like image recognition and NLP. Like I told you, if you have a problem statement where you have to identify what is the particular image, or you need to identify what is a speech signal, right? You have this face unlock, which is nothing but the image recognition problem. You have voice unlock, that is nothing but the natural language processing problem, right? So you see, all these problems cannot be done by machine learning. The reason is you have a lot of different features and a lot of different parameters in your image and your voice signal than what you give otherwise as a tabular input to a machine learning, right? So machine learning cannot handle the inputs which are of the form image, video, or signal, right? So this is number one limitation of machine learning. Second, another reason is the same reason actually. When we're talking about image and when we're talking about voice and all, they have a lot of different parameters, or you can say the dimension of the data is very high, right? If we say we have a say 2x2 image, so actually the input what we have is nothing but 2 into 2, that is 4. I mean, you can say 4 different pixel values, right? But in reality, if you see the image dimensions, it is generally of the form 1024 cross 1024 or 2048 cross 2048, right? Then just imagine the number of data. Just imagine how big the dimension of the data is, right? So that is the reason why again machine learning cannot be used. Summarizing what I have covered in the previous slide, if you see I have a table which is an input to the machine learning, and I have only 2 features, and based on those 2 features, what do I mean by 2 features? Let me just go back, let's make it simple. Suppose we are just having the same problem, right? We want to classify what type of flower it is, the input, and we have only two features, right? And based on these 2 features alone, we have to make a prediction. So basically this is a 2D input format where I have feature 1 and feature 2 and I have to make a prediction, right? And whatever the classification is, right, you might have seen about the decision boundary. The decision boundary actually helps me to make a boundary between class A and class B. Say if it's a 2-class problem, I have to make a decision boundary between class A and class B. And you see the decision boundary in this case is a line, right? But now if you see I increase the number of features from 2 to 3, you see now it is a XYZ space, which is a 3-dimensional space. Now can you tell me, can a line actually form a decision boundary? No, the line cannot form a decision boundary. Now I need a plane, right? I need a plane in the XYZ space to actually distinguish one space, or you can say one class from another class. Okay, now this is the scenario when I have 3 features. Now imagine, like I told you, in case of image, where I might have 2048 cross 2048 input dimensions, then can you understand how complex the entire space would be, right? It is much more than 10-dimensional. Even like I told you, it is 2048 cross 2048 example, right? In that case, having forming a decision boundary is very difficult. It's actually impossible, right? So machine learning is definitely not good enough for solving problems of image recognition and NLP. Machine learning cannot solve. Now we look at another limitation of machine learning. Another limitation is when you give the input to a machine learning algorithm, you also need to specify the different features. Again, coming back, it's the table. When you visualize the table, you cannot expect the machine learning model to understand or learn without giving these features, right? So it is your responsibility as a user to give these features, give these columns, column 1, 2, 3, 4, and only then the model is learning. That is what we have seen in prediction of the house rent and all those things, right? But if you talk about image, or if you talk about voice, what are the different signals you can you can give? You really can't do anything. You just have to give an input which is of the form and of an image or a voice, right? So that is the reason why deep learning comes into play, because deep learning has a specific capability through which it can automatically extract the different features from an image. I hope I'm clear on this, right? So again, coming back, sorry, just pardon me, I'm just using this example as a reference example. So we saw when in machine learning, the user has to explicitly give these features as an input. But just imagine if the input to the machine, or you can say the input to the AI model is an image. It's an image. And what is the image? Image is nothing but a matrix, right? Having some pixel values. Then in that case, you see this image and this particular table is so different. And then how do you extract the features? So that feature extraction process is something which is inbuilt in deep learning models. Now, because of this feature extraction, implicit feature extraction ability of the deep learning, we can actually use deep learning on complex data sets like image, audio signal, and videos, right? So I hope I'm clear that there are certain tasks which machine learning cannot do, right? There are certain problems which is beyond the capability of machine learning, because number one, I told you dimensionality, it cannot handle a very big huge dimension, and second, an image you cannot give it into a tabular form, right? So these are the two limitations of machine learning, and that is where the entire concept of deep learning comes. So finally we're getting to introduce to you all to deep learning, right? So yeah, so now talking about deep learning, we saw the basic motivation was when we have data sets like images or videos or audio, there machine learning cannot be used, and there we use deep learning. So if you see the problem statements, this is the problem statement, very simple. For a human, it's very implicit to understand what is a dog, what is a cat. But how do you transfer that sort of capability to a machine? So this is what deep learning problem is all about, right? Now, so the entire process, how it happens is, the training phase and the testing phase, everything is same as compared to, if you compare deep learning and machine learning, everything happens the same. The only difference is the nature of the inputs and the complexities what deep learning can handle and what machine learning can't, right? So we have a training phase where we give a lot of different types of dogs and different types of cats to the machine, and there's a training process, right? So what happens is, in the deep learning model, the only difference is, when you give an input image, say for example, I gave this particular input image of a dog, there is an automatic feature extraction happening in the deep learning model. And what do I mean by automatic feature extraction? Because you're giving only an input image. You are not giving an input which is of a tabular form, which has multiple columns. Each column is a feature. That was the responsibility and the headache of a user. But right now you're only giving input image. You don't care. You don't have to do anything else apart from your end. So there's a feature extraction process which is handled by the deep learning model itself, which is going to extract various features of the image. And in the image, I mean by dog, right? So various features, what do you mean by various features of the dog? One can be the eyes, the nose, the tail, the ears, right? So these are the various features which have to be extracted from the image. And this is the headache of the neural network now. This is not the headache which you had on the user side in machine learning case, right? And once those various features are learned, and only then I'll be able to make a prediction, okay, whether this is a dog or a cat, right? For example, just on a very layman term, how do you say a dog is different from cat, right? How do you say that? When the eyes of the dog is not matching the eyes of the cat, the nose of the dog is not matching the nose of the cat, and so on, and only then you come to a final conclusion that dog is not equal to cat, right? So, and you have to understand the bottom-up approach, where in the bottom I am focusing on the smaller features, right? What do I mean by smaller features? Say for example, eyes, the nose, and the ears. And then what is one level higher feature? It can be a face, okay, the face of the dog. And what is one more level higher feature? That can be the entire body, right? So what I mean to say is, when the eyes itself are not matching, then I can straight away conclude that the image is not of the dog. But if the eyes matches, then I have to look, is the face matching? If the face is matching, then I have to see is the body of the entire test image matching that of a dog. So if you see, there are various levels of feature extraction, and once at eye level, and then at the face level, and then at the body level, all of these are matching with the dog, then I can say, okay, this particular input image is that of a dog, right? So I hope I'm clear on that. So now looking at the extraction process, like I told you, you have an input image, you have to learn the features, the various different features, like I told, eyes, nose, tail, you know, all those things. And once the features are learned, it then makes a prediction. It then makes a probability that 95% this might belong to dog class, 3% it might belong to cat class, 2% something else, right? And because you see the highest probability or the highest voting, or you can say the probability is for the dog class category, finally the input image is predicted as dog, right? Now this is how the entire classification process of deep learning happens, right? So what happens now when you are training the deep learning model, like I told you, you have to give all sort of images, all sort of images of different class, right? It can, in this case, it is, I think, horse and dogs. Okay, so you give different different types of images of horse, and then you give different types of images of dogs, right? And then what the machine learning, what the deep learning model in this case does is, in the first, so you see the training phase or the learning phase happens over multiple iterations, right? So if you see in the first iteration, I made a decision boundary, and the decision boundary, if you see, it doesn't correctly classify all of them, all the training samples into the respective labels. There is some error, right? There's an error because there's an error one because this is classified as, this horse is classified as dog, and there's this another error because this dog is classified as horse, right? And in another iteration, in the subsequent iteration, you see the model has improved a bit, because now the horse has actually come to this particular horse class, but the dog is still here. Finally, in the last iteration, you see it has classified all of these things into the respective labels. So this is when we say the model has actually learned. So this entire thing actually represents the training phase, right? Like I told you, training phase happens over multiple iterations. Over the first iteration, the model did a good job, but that was not enough, right? It still goes on, and finally gets all the classification right. And this is where we say the machine has actually learned from the input images, right? Now, talking about how deep learning works, I told you deep learning is all about mimicking the human mind, right? And that is why we actually mimic what the neurons we have in our mind, in our brain, right? We have the similar set of implementation for the neural networks for solving some of the deep learning problems, right? So I think you might have been introduced to the basic concept of what a neural network, what a perceptron is, a single layer perceptron. You know, I'll not be digging too much deep on this to avoid the redundancy, but just to say, so we have all these inputs, right? And then there is a you can call this as a hidden layer or something, right? And then you have the final output. Output can be Y or something. Okay, so you see each of the input, when we talk about an image, right? Like I told you, say if we are considering an image of say X cross Y pixels or dimensions, then each of those what do I say? I mean the matrix, right? It's basically a 2D matrix. So when I have to give that as an input to the neural network, it has to be stacked up in an array. You get me, right? So basically, if it's a 2 cross 2, 1, 2, 3, 4, right? 2 cross 2, if it's a matrix, or you can say an image, I have to give 1, 2, 3, 4. All of them has to be stacked in an array, and then that will be given as an input to the neural network, right? And then each input is assigned a weight. These weight matrices are essential to understand what is the, I mean, how much important, how importantly is the output depending on each of the input, right? So that is what the entire learning process is in neural networks, or you can say in deep learning. We'll be assigning weights, right? And once the weights are learned, we can say the training process is done, and then this model can be used on a new image, or you can say a test image, right? That is when the model is actually applied to other different types of inputs. Am I clear so far? Hello? Okay, assuming it's all cool so far. So yeah, so this is the basic structure of a deep neural network, right? Why do we call deep neural network? In the previous case we saw there was just one hidden layer, right? But when you have multiple hidden layers, it becomes a deep network, a deep neural network. So this is the input. This is the input layer where we are actually giving the input, right? This is the output layer, okay? And then you can see these two are the hidden layers. So all the feature extraction and the process of classification happens in this hidden layers, right? So you as a user have to give the input here and get the output here, right? So these things are all handled by the deep learning model. Now we look at the deep learning use case for face recognition. Like I told you, we have the input layer, we have the output layer, right? Clear so far? So you see, input, it will basically be an image of a person, and that image of a person is going to be a matrix. Basically any image is a matrix ultimately, right? So what I'll be doing, I'll be giving all of that as an input in this input layer, right? So all that 2D array will be converted into a 1D array and will be given as an input in this input layer, and in this output layer we'll be getting the prediction, okay, whose face is this, right? That is the output. So I'll tell you what happens on a very broad level. The process of any object recognition, whether it is face recognition or digit recognition or any sort of object recognition, the process is, you will have, like I told, you will have some feature extraction process, and based on those feature extraction process is where you actually it actually helps you to classify whose face is this, right? So we'll have this feature extraction process at the hidden layer 1. You can see this will be the hidden layer 1. Okay, actually this is the output of this entire thing is hidden. Okay, wait 1 second. Okay, so we have a lot of pre-processing also going on here, so that is why this entire thing becomes the hidden layer 1 and this entire thing becomes the hidden layer 2. Now there are various features of the face, right? Now like I was telling you, in case of a dog, it will be very similar in case of a human face also. There's no difference. So when a human face is given to a face recognition machine, the hidden layer 1 will extract the features, very detailed features, like say your eyebrows or your eyes or your nose, right? So that your lips, your ears, so that will be detected in the hidden layer 1, the precise details, right? And then in the hidden layer 2, you will be extracting the bigger, or you can say the more abstract features, like your face, your entire face, your face shape or your hair. You get it, right? So that is how the entire process of recognition happens. We'll learn more about it when we understand how DL works. Similarly, this is another use case where we actually use deep learning to understand the handwritten digits, right? When somebody is giving a handwritten digit 7, we need the model, we need the machine to say it is actually 7. So this also happens in a similar way. We have a hidden layer 1, we have a hidden layer 2, and then we have something called as fully connected layer, right? I'll talk about more in detail about the entire architecture. It's called the convolutional neural network. So convolutional neural network, CNN, is a specific type of deep learning model which is used for object recognition problems. Okay, in fact, it is the best available solution out there in the market to solve any sort of object detection problems, right? So you have various deep layers, layer 1, layer 2, then you have the fully connected layer, and then when we're talking about this handwritten digits, right, we have 10 classes, 0, 1, 2, 3, all the way to 9, right? And for each of those class, you will have a prediction. So this is, say, 0 for the class 0. What is the probability that this 7 image, right, is actually 0, or you can say belongs to class 0, is actually 0. Then you have something, and then you finally see that input image 7 has the highest probability for class 7, that is 0.8. So 0.8 is the highest probability among all the other classes, and that is why you say the classes at the image, what you see input here, actually belongs to class 7. So this is how this entire class voting happens. I'll go in more detail, but just to give you a brief use case of deep learning, this is how the entire process happens, right? Okay. I'll just cover these things very quickly. Deep learning applications. So we have seen machine translation. You know, you can have translation from one. I'm sure you people might be aware of the Google Translate app, right? So back when I was doing my internship in Japan, so the thing was nobody knew English there, and even in on the food packets and items, everything will be written in Japanese, right? then how do you know what are you buying? So there was this very useful and very handy application called Google Translate. What it does, you just have to capture the picture of whatever is there written in Japanese, and the model actually processes it and gives you the English translation of that, right? So this is a very useful application of deep learning. Again, you might while you're taking selfies or something, it is able to form that box over your face. And in some cases, if you have customized your mobile with giving your name to that particular box which contains your image, then it can actually even predict whenever it sees the next time, right? So these are all our applications of deep learning, right? So Google Lens is a very particular application of deep learning. I heavily recommend you to people to go and Google about this Google Lens, right? I'll not be going much deep into these things. So yeah, so now we are coming to something called as convolutional neural network, CNN. Now, when we're talking about deep learning, also deep learning is again a very broad topic. But then, like we knew about machine learning has various algorithms like decision trees or naive Bayesian algorithm or support vector machine. Similarly, deep learning will have different architecture, or you can say different algorithm, right? And one of them, what we are going to be looking at today, is called the convolutional neural network, CNN. So CNN is the most popular and the most, you can say the best solution out there to solve any sort of object recognition problem. So anytime you ever want to solve an object recognition problem, you know where to go. Okay. So now CNN is basically convolutional neural network, is a deep learning algorithm which takes an input image, okay, assign the importance, that is the weights and the bias, to every input, okay, every input, that is nothing but every pixel of the image, and it should be able to differentiate one image from another, okay. And so there are certain benefits of using convolutional neural network. The one is like you saw in machine learning algorithms, and even I think I took day 2 session 2 on association rule mining for a priori, right? You might remember that I actually did a certain level of pre-processing before actually giving the data to the model, right? And we also talked about importance of pre-processing, the data cleaning process, right? Where before giving the input to the model, it is the responsibility of the user to clean the data or to do certain level of pre-processing. The best part of convolutional neural network is the pre-processing required in case of CNN is as good as zero. So you don't have to do any pre-processing at your end. If you have an image, just directly give the image to the CNN model. So this is the benefit. So all the pre-processing is taken care by the hidden layers and the deep neural networks. So from your side, the headache is minimized to the maximum extent, right? And then there are something called as filters in CNN, which we will look ahead, right? And the responsibility of the filter is to extract each features from the object, like we saw, right? The deep learning model actually has this implicit feature extraction process, where it's the responsibility of the network to extract different features like the nose or the eyes, or right, from a dog's point of view or from a human face point of view. So the model has certain filters which actually extracts those features. So this is the short, or you can say the architectural view of the convolutional neural network, where I have the input image, and then finally the output will be the class, whether it's a car or whether it's a tree, right? What is the object? And so there are various layers which are used for convolutional neural network. I will be talking about each layer and the importance of each layer, right? So we have first is called the convolution layer, where we do a process called convolution. Now, I'm not sure how many of you people are actually aware of convolution. I'll be telling about that. So the first convolution layer actually does a mathematical operation called convolution. Then there is a second layer called pooling layer, and then there's another, and then this entire thing actually repeats, convolution layer, pooling layer again. So you can see this entire thing is repeated. And finally, we have the fully connected layer. This fully connected layer is where actually the class voting happens. I'll just go back to show you the class. 1 second. So we saw this fully connected layer over here, right? So we saw this class voting where each class is actually assigned a probability that this input image belongs to that particular class, right? And you see for this input image 7, we got a highest probability 0.8 for the class 7, and that is how we actually told, I mean, we actually came to a conclusion that this particular image belongs to class 7, right? So this is a fully connected layer. This is a fully connected layer in this case, right? So I hope the architecture is introduced to you all. Now motivation for CNN. Now what is the motivation? Like I told you, whether we are doing a detection or a classification task, okay, number one, we are talking about different types of data set, right? We talked about deep learning being able to solve problems in the domain of computer vision, where it deals with images, right? Deep learning is also used for the domain of natural language processing because it deals with audio data types. And then it can also and then we also have this sentences and text. Again, NLP is used there, right? So you see all these data types cannot be supported by machine learning, and that is why machine learning is not, you don't get to hear machine learning about, I have used machine learning for image processing or for autonomous vehicles. No, that's not the case. So that is where I'm again iterating, that is where the power or the concept of deep learning comes, right? So now if you see, we'll be talking about each of these inputs in detail. When we're talking about an image, right? So the image can be given as an input, and the output can be a motorcycle, which suggests, or you can say the problem can be what is the object in this image, right? So the answer you see is a motorcycle, correct? If the input is an audio, what can be the output? The output can be, you recognize whose audio is it or whose voice it is. That is predominantly used in the voice unlock system of mobiles and laptops, right? Music classification, it can help you to classify music, and it is also heavily used in raga detection. Like there are so many different types of raga. You give a raga, a particular type of raga, the deep learning model has to tell, okay, which type of raga it is, right? And then the speaker identification, like I told. Similarly for text, you have this you might be aware, right? In the Google in the Gmail, some mails automatically get put in your spam folder while the others are sent as important. Why that happens? That because the model probably is using some words or some keywords. If that keyword is present in the either the email ID or the subject or the content of the mail, it says, okay, send this mail to the spam, right? So this is how I just give an example. With the kind of inputs we have for deep learning, these are the possible types of operations or the possible type of problem statements we can have. Now, how does a computer actually work with an image or an audio or a text, right? So let me just get here. So there are various features of an image, and similarly there are many features of an audio. Okay, now when we talk about features of image, those people who are aware or who have a very strong mathematical background in computer vision might understand. So there are different features, or you can see the features which can be extracted from an image, right? How do you say one particular image is very different from another image? I'm not saying not visually, because visually as a human we can say, but how can a machine tell? So one good way or the easiest way of telling is histogram, right? If one image is different from another, histogram of that particular image will be different from histogram of another image. Histogram is nothing but this distribution of the pixel values, right? Then we might have something called as HOG feature. HOG is nothing but the histogram of oriented gradients. Now I'll not go very deep into each of these because these are very domain centric features and terms, but the point I'm trying to see is, if one image is actually differing from another image, their HOG and so SIFT here actually stands for the scale invariant feature transform. Now obviously you people are from very diverse backgrounds, so I'll not go in depth in each of these, but then the point I'm trying to say is these features are actually ultimately used by the computer to distinguish one image from another, right? So if one image is different from another, there all these feature values will also be different from another, right? Similarly, we'll have audio features, right? This audio features basically spectrogram. Spectrogram actually tells you the visual representation of the spectrum of frequencies of a signal, right? So here you can see what are the how the frequency is actually varying as the voice as the audio sample is varying. So this is how the machine is going to learn about the audio, right? So if two different audio samples have exactly the same spectrogram, then we can say, okay, there's a probability that those two audio samples might be same, right? Then there is something called the zero crossing rate, ZCR. It actually tells how many times your audio sample is crossing the zero signal, or you can see the zero amplitude, right? So these are some very technical and domain centric features which are used by the machine, the deep learning model, to distinguish, or you can say to distinguish one audio sample or an image sample from another, right? So now coming to challenges of features. Now I have told you what is the importance of feature. Only by extracting the feature can a deep learning model tell that, okay, this object is so and so, right? Now coming up with a feature is difficult, time consuming process and requires domain knowledge, right? Like I told you, all these features, it is only an expert in that particular domain might be very thorough with all these concepts, right? But a person who just wants to implement the deep learning model just to know that what is the, whether a dog is classified as a dog or not, then for us to deal with the features becomes very, very difficult, because we do not have that sort of an expert knowledge, right? And a lot of time is actually spent during tuning the features, because if we get an audio sample, right, then we have to tell the machine, okay, you extract the spectrogram feature, you extract the MFCC feature, you extract the flux and the ZCR feature, right? So if a user is not aware of all these features, he might actually miss out few things, and that might actually downgrade the quality of his classification. So the whole idea is, whatever you saw in all these slides is very technical, and when a user is using the deep learning model for the classification purpose, let him not deal with what feature is to be extracted, right? Don't give the headache of the domain knowledge expertise on the user who is ultimately going to be using it, right? So now we have the various steps of feature representation from input to output, which happens in a deep neural network, or you can say CNN. So we have a low level sensing. Like I told you, what exactly low level sensing is, actually it is going to be taking all sort of inputs, and it's going to just see whether the pixel values are correct, or all that sort of a thing. Then you have, like I told you, the benefit of a CNN network over any other network. I think MLP, multi-layer perceptron or a single layer perceptron, if you compare the benefit of CNN, is that you do not have to do any pre-processing from your end. The pre-processing will be taken care by the network itself, right? Then comes the most important feature of feature extraction. Like I told you, it is the headache of the network to extract features, right? And like we saw here, there are different features, but now I don't know, I don't have any knowledge about the features. So in the feature extraction process, what features are to be extracted and how are they to be extracted is the headache of the deep learning neural network. It is not my headache, right? So I am actually saved from that requirement of a domain expertise. Then there's something called as feature selection, which actually selects the relevant features for the classification. And finally, we have the prediction, right? So if you see this, this entire process of feature learning, what we say that instead of designing features, let us design some features which actually learn the features. The point I'm trying to say is, in this case, like what we saw, instead of us as a user to understand what all these features are and to extract, we will rather develop an entity, or you can say a black box sort of a thing, which will automatically know what to extract and how to extract, right? So as an end user, you do not have to touch this like domain and the concept at all. I think we have taken this, we have seen how this face recognition happens, right? So you can see there's this image, right? Image will be a 1D array actually, and then these are the hidden layers, and finally you have the classification. So in the first hidden layer, very detailed features will be extracted. In the higher layers, a more abstract or a more higher level feature will be extracted. And then the feature extraction process happens in these hidden layers, and then this entire thing is actually the learning phase, right? And then finally we have the prediction. So yeah, now talking more about in detail about the convolution neural network architecture. So we have the input. Then I told you we have the convolution layer. I'll talk more about it, what convolution layer is and what convolution operation in general is. Then we have a non-linearity layer. Then we have a pooling layer, and then we have a normalization stage again, and this is optional. And then finally we have the output layer. Now let me this is again a very important diagram depicting the architecture of CNN. I think any doubt, please feel free to question me right there, right? So this is the architecture of CNN. So like I told you, you'll have the input, and then you have something called as convolution layer. This ReLU is the non-linear layer what we saw here. I'll tell more in detail what ReLU is. So this non-linear layer is nothing but ReLU. Okay. Okay, somebody there?
Yeah, sir, only one doubt I want to ask with you, sir.
Yeah, tell me.
Sir, please elaborate what's pooling here? What's the functionality of pooling?
Correct. So I just wanted to give you a snapshot of the entire architecture of CNN. I'll come to each of what is convolution layer, what is ReLU, what is pooling. I'll come to each one of that.
Okay,
right?
sir. Thank you, sir. Thank you, sir.
Okay, this is just to give you a snapshot of what you can be looking forward to in the next few slides, right? So this is the entire architecture of CNN, where we have convolution layer, ReLU, non-linear layer, pooling layer, and then this entire thing is again repeated. So this is one hidden layer, and when the same hidden layer is repeated again and again, I can repeat it many times, doesn't matter. Then finally I have the fully connected layer, where I told you the class voting happens for each class. Class voting is basically assigning the probability, and finally we have the classification. So this is the architecture of CNN. Now let's come to each of these layers. So we'll be covering each of these layers in details. So before that, let me talk. Now we'll be looking at what convolution layer is, right? But before that, we'll talk about the convolution operation. So the convolution operation is actually defined as this, right? F star G is defined as the integral of product of two functions after one is reversed and shifted. Okay, so this, let's not get into the math of it. Explaining it in terms of how the operation happens will be easier, right? If anybody wants to dig deep into the convolution operation, they can. So I'll tell you how the convolution operation actually happens. So we have a matrix, the bigger matrix over here, right? So you can see the bigger matrix is nothing but A, B, C, D, all these values till KL. And in convolution, you have something called as filters. So this is the, or you can say kernels. These are called the convolution kernels. So convolution kernel has a value W, X, Y, Z. So both are matrix, right? So now what is entire, now this is all mathematical. I'll just give you a trace so that you understand what each of these equation mean, right? So you see, this is the parent, or you can say the bigger matrix, and this is the convolution kernel. So what do I mean by convolution operation here is, when I convolve this kernel on top of this matrix, I get something like, so you see this has a window of 2 cross 2. So I'll be doing this first here, okay? So this basically means I'll be multiplying each of the corresponding elements and then adding the entire thing. So what happens when I superimpose this kernel on top of this element of the matrix? I get AW, right? A into W plus B into X plus E into Y plus F into Z. Okay. Now what I do, I actually shift this kernel by 1. So now it was here. Now it will shift here, right? The mouse is visible, right? I hope the trace is clear. So now for the second one, this becomes W into W, B into W plus C into X plus F into Y plus G into Z. So this is what we get over here. So this will be the second element. Now finally we'll be moving this kernel over this part, the last part of the first row. So you get the CW into DX. You get it, right? And similarly, we can bring it down. We can bring this kernel on the second and third row also, right? So same process you'll get. So this is what the convolution operation is, right? So I hope mathematically you understood what convolution operation is, correct? Now we will see how does the convolution operation help in extracting feature, or does help in the object detection algorithm itself. So now let me talk about, we have something. Now I was talking about feature extraction, all these whiles, correct? Now we will see how exactly does the feature extraction happens. So the entire feature extraction, what I've been talking about, right? When you give an input image of a face, the features of eyes, nose, lips, all that thing has to be extracted. So that happens using the process of convolution. Okay, now let me explain. So we have an image. Okay, the image has some values, 1 1 1 0 0 0, all this is the image value. We use a feature filter. I'll dig more deep into why this filter is required and what is the significance. But if you just see, we're just following what convolution operation is mathematically, right? Just to make you aware of what convolution is. The filter value is 1 0 1 0 1, all these things, correct? So if I convolve this over the first part, right, what do I see? I see 1 into 1, 1 into 0, 1 into 1, and then I have to add all these things, correct? So you see what I ultimately get at this particular, this is the resultant matrix, or you can say the convolved feature. Okay, so you see 1 into 1 is 1 plus 1 plus 1 plus 1, so 4. So that is why I get a value of 4 over here. Okay, now I will move this entire thing to this particular, to the second, third, and fourth column, and then whatever value I get will actually come here. So that is how the entire process of convolution happens. Now now coming back to why convolution is essential or is required in the process of object identification, we will come here. Okay, so let me come back here. So what happens, we have an input image. Okay, like I told you, the feature extraction process happens automatically in deep learning. Now automatic, let me explain what is automatic, because it should not be, at the end of the day, it should not be like a magically it happens. So what happens when I give an image of a face over here? So imagine this is the face of somebody. Okay, when I give a filter over here, I basically I know, or you can say the model knows that there are multiple features which can be present in a face. Can anybody tell me what can be the various features of a face? Anybody? Hello, am I audible? Santosh sir, Mercy ma'am.
Yeah, you're audible.
Okay, actually I can't see the.
Yes, Ishak.
I mean, I can't see that. So you can unmute. Yeah, exactly. You can just unmute yourself and say. Okay, so basically the features of a face can be eyes, nose, lips, ears, right? So what these convolution operation actually helps me to achieve is, I will have one filter for detecting eyes. I will have another filter for detecting nose. Similarly, I will have another filter for detecting ears. Okay, so what this does is, now when I for example, a person, there is a person who doesn't have eyes, for example, just saying that, or you can just say that eyes is not there. So what happens is, basically, okay, let's assume he has eyes first. In first case, he has eyes, right? This is a very absurd example, please pardon me. So when I move the eyes filter on top of the image, which is nothing but the face of the person, so say example, eyes is present in this part of the image, okay, this part, and when I'm doing the filter, when I'm moving the filter on this part of the image, I get a very high value, and that high value can be very high, probably just say 9, say all the things are 1 and it just says 1, sorry, 9, my bad, my 9, right? And say this part, this lower half part of the face actually contains, say, lips. Okay, now when I move the filter of eyes on top of the portion of the image which contain lips, I will get a very low value. So the convolution value, this is the convolution value what you see, right? The convolution value which I'll get for this particular portion of the matrix will be very low, which basically tells me that when I move eyes filter on a portion of an image which has eyes, I will get a very high value, which indicates that eyes is present in this part of the image. But when I move this eye filter on top of a portion of a face which is not having eye, then I get a very less value, which indicates that eye is not present in this part of the image. So I hope I hope it's clear that why filters or why this convolution operation is important. Correct? So the convolution process is important because when I convolve and get a value, higher the value, what it signifies that what that filter is used for, say this filter is used for eyes, it says the probability of finding eyes in this particular region is very high. That means I have detected eye, or you can say I have detected the eye feature from the entire image. Now suppose somebody is not having an eye, or you can say somebody, it is a backside image, it's a head, right? The head facing the opposite side, I mean eyes facing opposite side. Then if you see, if you move the eye filter over the entire image, you will not get any high value. You might only get 1, 2 or something, which basically signifies that from that particular image, I could not, or you can say the model could not detect an eye. So this is the entire significance of filter. Correct? I hope I'm clear. So every feature will have a corresponding filter, and I do a convolution operation on top of the entire image to find whether that particular feature is present in the image or not. That is how I am going to be extracting. So I'll just go back, pardon me. So that is how I'm going to be extracting at the initial layers the presence of eyes, nose, lips, etc. And then when I go to higher level, I will have higher level features. For example, say jaw or say hair and all those things. So I hope that I was talking about this feature extraction process and all. I hope it's clear. So now you understand the significance of convolution, right? So only when I convolve the filter for that particular feature over the entire image, I come to know whether that particular feature is present in the image or not. So why convolution is explained, right? So now if you see, we have this hidden layers. Okay, when I actually do a convolution, this all this entire thing actually falls down to this particular point. I mean, it is downsampled, right? And then I actually move the filter. You can see I have shifted the filter a little bit by one cell, and then I'm going to be multiplying, right? And all the things, if you see, are sorry, if you see is all added, right? So ultimately I will just get, see the entire filter. If I move over this image portion, I get one value. So similarly you get one value over here. So this process actually helps me to tell that if eyes is present in this part of the image, and I'm moving a eye filter on top of it, I'm not moving a ear filter, or I'm not moving a say lips filter, I'm moving an eye filter and eye is present, so this value will be very high. But if say eye is not here and I'm moving eye filter over here, I will get a very less value, which says that eye is not present in this part of the image, but eye is present in this part of the image, right? So I hope the entire feature extraction process is explained. Now we have something called as non-linearity layer. What this non-linearity layer actually helps us to do is, mathematically, if you see what are linear functions? Linear functions actually are nothing but when you see the output is a combination of linear combination of your inputs, right? But if you see, I think have you people been explained about the AND OR gates, right? I'm sure you must be explained to the AND OR gates and how single layer perceptron can help you distinguish between AND and OR, but I mean solve the problem of AND and OR gates, but cannot help you solve XOR gates, correct? The reason is because AND or OR is a very linear problem. But then when you are solving a problem of XOR or more complex problems like image recognition or face recognition, you see it is not it's not a linear function, or it's not a linear operation. So that is why we have a non-linearity layer assigned, and that can be a ReLU function or sigmoid function, right? I'm sure all of you must be knowing what is sigmoid function. It actually squashes the output between I mean, if it is greater than 0, you'll have the value of the sigmoid function will be between 0 and 0.5. Similarly, if the value of x is negative, the value of the sigmoid function will be between 0 and minus 0.5. So non-linearity layer is actually introduced in the deep networks to ensure that your entire neural network is not a linear operation, right? And then we have the pooling layer. Somebody was asking what is the pooling layer, right? So now we come to the pooling layer. So pooling is actually used to shrink the image size and dimension. Okay, So now what actually happens is the reduction depends on the window size and stride. Now what I mean by window size and stride is, again, we use the kernel for convolution, right? We will be using another kernel for pooling. Okay. Now say for example the kernel is this 2 cross 2 is the kernel size. So that is why you can see these are different kernels. Okay. So that is the window size. And what I mean by stride, let me just go back. If you see here, now this was also a kernel. In the convolution case, the kernel size was, if you see, it is I think 5 cross 5, correct? So the window size will be 5 cross 5. Now if you, what do I mean by stride? If you see here, the filter was actually moved or shifted by one pixel value. So here the stride is 1, right? Now in this, coming to this particular case, the window is actually the window size will be 2 cross 2 and the stride is actually 2. So here will be my first filter, and when the stride is 1, I actually move by 1 cell, but when the stride is 2, I actually move by second cell. So here, you understood, right? So I think this is clear. So the window size and stride is clear. Now what actually happens in the pooling case, pooling actually has 3 varieties. We have max pooling, min pooling, and average pooling. So what max pooling does, for this particular window size 2 cross 2, I have to take the maximum value present in this window, that is 6. So now I have 6. Now I move the filter by 2, right? Because the stride is 2. Now I come here. Now the maximum value over here is 8. I come here 8. Similarly, here I get 2 and here I get 4. Correct? So I hope it's clear. So pooling is actually a way of downsampling your entire image. Okay. Now what is the objective of the downsampling? Is see these values of the array, or you can say the matrix, is going to give you some sort of a probability that something is present, or you can say this 4 pixel values might be representing the representing some feature. Say if this entire thing is a tree, right? So the combination of these 4 pixels might say give you, for example, it is representing a tree, this might be representing a house, this might be representing water, something like that, right? But then once I have extracted the features and I know where tree is, I know tree is here, I know the lake is here, I know the car, I know the house is here, I can actually move on to the bigger, or you can say other features, which are the higher level features. So I do not need the entire pixel value. I will just work with a representative value for this entire feature. So that is why I work with 6 and I work with 8 and 3 and 4 here. Correct? So the benefit of pooling layer is, let me go back to this face recognition example. So you see, once the lower level features, like you can say lips or eyes or nose, are extracted or are detected, then I can downsample my image and focus on other bigger features like jaw, like chin, like hair, right? So this downsampling actually helps me to focus on other features which are at a higher level. Okay, so I think that's clear. Now coming to how CNN works, right? So now we will look at how exactly CNN works with the concepts we have seen so far. So you see, what when we are having the handwritten digits, right? The X can be here, the X can be here, the X can be here. You can see there are different ways of writing X. A person can write X in many ways, and a machine should be able to detect all these scenarios as X. Similarly for O, if you see, there are so many different ways of writing O, and when you give it as a pixel representation, you see they are so different from each other, and yet the system has to say it is O. It is very difficult, because how machine works is they actually work by exact comparison of pixel. So when you do exact comparison of this particular image and this particular image, you know they both are not equal because the pixel values are not equal. So the model might actually end up saying this is not O. But that is not what we want, right? So what we want is, in any O you give, the model must be able to predict it is O, right? So how this is done is, now this is what I was saying. This X is not equal to this X. So if you give it to a computer, right, the computer might see all the black elements as -1 pixel, all the white as some value which is 1, actually not 1, something which is non-zero. But when you do a pre-processing, right, you ensure that all the black ones are -1 and all the non-black ones, it can be any color, but what we say non-black is 1. This is just for easy representation, right? So if you see this particular x is not equal to this particular x, so if you give it to a traditional machine, the machine will not be able to identify these two as x, because these two are not identical, right? Because computers do exact matching. That's why this x will never be equal to that particular x. So how it actually happens is CNN will break this entire image into features. I was talking about features all this while. Now finally I get to explain what feature is, right? So if we see this entire x can be broken down into 3 features. The first feature can be the diagonal, which is extending towards the right. Then we have a cross, and then we have a diagonal which is extending towards the left. Similarly, if you see in this particular image also, these features are present. So instead of doing an exact match, like in this particular case where we know the output will not be in our favor, like I told you, CNN will extract features from the images. So in terms of face, we knew it was nose, eyes, all the thing. But in this particular example, in this particular example, yeah, for example, the big X, we could actually break it into further small features. And if this particular small feature is equal to this particular small feature, this particular small feature is equal to this, and then is this, right? Similarly, we have for this one and this one also. Then we can say when all the sub features are matching, we can say this X is equal to this X. So that is how the classification process happens. So for each of these features, I told you we'll be having a filter. So one filter will be responsible for extracting this feature. Another feature will be responsible for extracting this feature, and for the third one, right? So if you see, this particular filter is responsible for extracting the feature of right diagonal. And similarly, this is for cross and this is for the left diagonal. I hope I'm clear, right? So now you can actually join the dots and look at the bigger picture where convolution is actually useful, right? So if you see now this particular, so now we are having an input image which is X, and we are having the CNN model has actually formed 3 features, 1, 2, 3, for extracting 3 different features of the input image, right? And now if you see what happens when now I'm doing the convolution operation finally. So when I'm convoluting this particular filter of right diagonal on this part of the image, right? On this part of the image, you see there's an exact coincidence. Right? 1 into 1 minus 1 into minus 1 will again be 1, minus 1 into minus 1 will again be 1, and this finally we do all these addition operation, and then we divide it by the total number of pixels in that window just to get an average, because ultimately we are dealing with probability, right? So we would want the value to be between 0 and 1. So when I do the convolution of this filter on this part of an image which actually contains this feature, you see I get a value 1. The value 1 says that this particular feature is definitely present in this part of the image, right? Now, okay, now if I were to convolve this part of this filter on this part of the image, you see this and this are not same. I will get a value somewhere here which will be less than 1. In fact, it will be less than 0.5. So what does the value of less than 0.5 actually signify is that this filter is not present in this part of the image and it is only present in this part of the image. That is what 1 here signifies, right? So I hope you people now understand how the features are actually represented, how each of the filters are represented using the convolution layer filters. So now we will actually be doing a convolution for each of those filters. So first, when we move the right filter, the right diagonal filter on the convolution on the image, we get this value. Similarly, when we do a cross feature convolution on the image, we get this set of values. So we have a stacked up stack of filtered images. Okay. So now we have something called as a normalization layer. Normalization layer is very easy. Like I told you, all that you have to do is, like, once you get this particular output, the convolved output, right? The convolved output. If you see here, we have some negative values. Now, I don't really want to work with negative values. I just want to make the model very, easy to understand for the machine, and I want to bring in some sort of a non-linearity. So what I do, I just convert all the negative values to 0. So you see all the negative values, whether it is high negative or low negative, everything is converted to 0. The model becomes non-linear. So this is the output of the normalization layer. And for the normalization, we use a rectified linear unit. The ReLU function is nothing but f of x is equal to x for x greater than 0, and it will be 0 for x less than 0. So basically, I'm just converting all the negative values into 0. Right? Now, for all the 3 images, what we got after convolution, when we applied normalization layer, we got these values, where the negative values were removed. Now we have the third layer, which is called the max pooling layer. Like I told you, in the max pooling layer, we take the maximum out of that particular window, which actually helps us to compress the images, compress the image size. And once some certain features are detected at the lower level, we can actually compress and have a representative value for this 2x2 value, and look at, and in the next layer we can look on to the other features which are at the higher level. So you see, this is ultimately the output of the max pooling layer. Fine. And then finally, if I had to summarize, so you see, I had the input image, I had the convolution layer. In the convolution layer, I had 3 filters. One filter for responsible for extracting this feature, another was for this cross, and another was for this left diagonal. Then we had the ReLU, where we converted all the negative to zeros, and the pooling, which took the maximum values and downsampled the images. And finally, we will have these set of 3 set of filtered images. So you see, the input is of a high dimension, and after these 3 layers, you can see the input is compressed. Each of the matrix is compressed, right? And this entire 3 layers, you can actually do it multiple times. You can actually have a stack of these input layers. So you can see it's basically deep hidden layer. So convolution, ReLU, convolution, ReLU, pooling, you can have this multiple times. So you see, if you do it multiple times, the dimension reduces even further. Okay. Now we have the fully connected layer. Okay. Now fully connected layer is basically whatever you got, right? Whatever you got in the previous output, right? Previous layer output, you stack it into a single layer. Okay. Now, once I stack it into a single layer, I have this concept of class voting, which I explained to you people. If something is X, if the input image is X, okay, there will be class voting, and which basically says the probability for X is 0.92, right? And the probability for class is 0.51, right? And all that we have to do is, whenever an input image X is given, and whatever is the highest probability for either of the classes, that is actually finally the image is predicted to that particular class. So here the class label will be X and not O. So I think I have reinforcement learning section after this, but we are short of time, so probably I can take this in the afternoon, right?
Excuse me, sir.
Yeah. Hello. Yeah. Tell me.
Sir, how we come to know about the probability that it's 0.92 or 0.51?
Okay. Okay. So you see here, for that I have to again trace back to the convolution part, right? Like I told you, if some feature, when I convert over the entire part, I'll get a 1 over there, right? Okay. Now if this was 0, for example, when I convolve this particular thing, this particular filter over 0, I will not get 1 over here. I will get some very less value, correct?
Okay, sir.
Which basically signifies that this feature is not present in O. O will have some other feature of its, correct?
Okay, sir.
Correct. So if you see, if we are actually using the X image, input image, and we are convolving it with these set of filters, okay, the values for this particular filters will be very high when I'm convolving it with X, with the features of X. Okay.
Okay, sir.
Similar process will be done for X with the features of O. Now, what can be the features of O? The features of O can be, just look at the direction of my mouse, right? It can be this particular arc, okay? Then this particular arc, and this particular arc. So basically, you understood, right? Or should I use a Microsoft Paint and hello?
Okay, I got, sir. Means for the phase that you can get its values.
Yeah. So when I'm convolving the feature of x on top of x, I get a matrix with very high values of 1 or close to 1. Okay.
Okay, sir. Now I got it.
When I convolve this x using the feature filters of O, I get a matrix of very low values. Correct?
Okay,
Now,
so it means with the help of convolution phase, we can get these type of values.
Correct. Now because I convolve this on top of the filters using filters of x, right? Arrows and the diagonals, I will get all these values as high values. Okay, close to 1. Okay.
Okay,
Now,
sir.
because I got all these values close to 1, the normalization layer and the pooling layer will not change the value much. It is just downsampling. So because I got a high value of 1, you can see most of these values will be close to 1. Close to 1. And when I average out and when I get the final prediction, I get a prediction of 0.92. But if I, now how did I get this value of 0.51? I just convolve this using the O features of O. When I do this, when I do the convolution with features of O, I will get a very low value for O class. That says it is 0.51. So that is how I come to know these class votings. So these class voting values will be high when I'm convolving it with features of X. And the class voting values will be low if I'm convolving it with features of O, because the input image is not O, it is X. Right?
Okay, sir. All right, sir. Thank you, sir. Thank you so much, sir.
Yeah, no issues. Sir, I think we are falling short of time. So I have covered, I wanted to cover two important architecture of deep learning. I have covered the convolution neural network, and I hope the entire process of convolution and how now it is not, I hope it is not a magic to to you or people now, right? It's not, nothing is magic. Obviously, there has to be a math and there has to be some concept behind object recognition. So convolution neural network is completed. There is reinforcement learning which is left. If time permits, I will take reinforcement learning. I will take reinforcement learning probably in the afternoon session, right?
Okay, so it means one more session you are going to conduct, sir.
If time permits, then yes. Sivaselvan sir or Santosh sir, what do you say? In the afternoon. In the afternoon,
Yeah, in afternoon, if you want, you can take for another half an hour or so. Initially
yes.
from 2:30 to 3.
Okay,
Yeah.
okay, all right.
We are also interested for this lecture, sir.
Okay, no, that feels good. Thank you so much. So, so deep learning, like I told you, is very broad topic, and I have just covered one part of it. That is the CNN. There is something else which is reinforcement learning. We'll definitely come back to that. So, looking forward to that session. Right?
One thing I would like to share some words with you, sir, if you permit me.
Yeah, sure, definitely.
Yeah, first of all, thank you so much, sir, for such a nice presentation and for such a nice lecture that you have conducted here. Really, sir, the lecture, the way of presentation is very good, and the way you delivered your contents, your way of communication, that is so clear that we could understand each and every word so nicely. And definitely, you are expertise in your field. So really, I'm very much impressed with your lecture, sir. Thank you so much.
Thank you so much, sir. Your kind words are only going to encourage me in future. Thank you so much.
One more thing I would like to ask you, sir. Can we have your email ID or any contact number so that we can have such type of sessions as we will be able to invite you as a resource person.
Sure. It would be my pleasure. So I'll just should I put it in chat or should I do it in a more formal way? What do you want?
You can ask. You